Hello and welcome to this video lab on soil compaction. For informational purposes, there are two procedures which allow you to determine the compaction characteristics of soil in the laboratory. There is Astm D698, which applies 12,400 foot-pounds per cubic foot to the soil. There is also Astm D1557. This is the compaction characteristics of soil using the modified effort, or 56,000 foot-pounds per cubic foot. In today's procedure, we'll be using Astm D698. Now, whether you're using the standard effort or the modified effort, you're going to need a rammer. In the standard effort D698, the rammer weighs 5.5 pounds. It drops freely for 12 inches, and it has a sleeve to guide the rammer to the soil. The rammer also has 4 vent holes at the top and 4 vent holes at the bottom, 8 vent holes in all. Now, when determining the compaction characteristics of soil using the modified effort, we're still going to use a rammer, but here the rammer weighs 10 pounds and it drops freely for 18 inches. However, it does have a guide sleeve and 4 vent holes at the top and 4 vent holes at the bottom. We're also going to need a cylindrical mold, a 4-inch mold for finer material and a 6-inch mold for coarser material. We're also going to need an oven, a scale, and mixing tools. Now, there'll probably be other pieces of equipment that we need along the way, but for now, let's head into the lab and begin our tests. In today's lab, we're going to be doing standard test method by compaction using the standard effort. What we'll do is we'll sieve our material through the 3/4 inch sieve to determine the amount of mass that we have on that sieve. We'll also sieve it through the 3/8 inch sieve, and then finally the number 4-inch sieve. Now, if you're not familiar with the way sieve sizes work, above the number 4 we have solid numbers, 3/4, 3/8 inches. Once we get into the numbers, which is below the 3/8, we turn into number 4, 8, 16, and so on. All that means is the amount of openings per square inch. Now, since today's soil has already been sieved through the number 4-inch sieve, what we're going to do is use the 4-inch mold. And again, this is the standard compaction test. Therefore, we're going to be using the 5.5-pound hammer, which is going to drop 12 inches. Now, there are 3 different procedures within Astm D698 that can be used. There's procedure A, which is used with a 4-inch mold. We do this procedure when the weight of the material retained on the number 4 sieve is less than 20% of the total sample weight. We'll use procedure B, which also requires a 4-inch mold, and this procedure is used when the weight of the material retained on the 3/8 inch sieve is greater than 20% of the total sample weight. And we use procedure C, a 6-inch mold, which is used when the weight of the material retained on the 3/8 inch sieve is greater than 20%, but less than 30% of the sample weight is retained on the 3/4 inch sieve. Now, you may recall a few moments ago we said that our material would be ultimately passed through the number 4 sieve. So therefore today we're going to be using procedure A. And again, procedure A is used when less than 20% of your material weight is retained on the number 4 sieve. So when we do this test, what we're trying to determine is the optimum density of our material. For example, if we were building a sandcastle on the beach, what we do is we add a little bit of moisture to that sand, and the sand begins to pack a little bit better. What's happening actually is that the sand is coming together better. Therefore, if we put sand into our mold here, that sand is going to take up a certain amount of space and it's going to have a certain weight. So let's just say, for instance, that the first time that we fill up our mold and we compact it, we have 3.25 pounds of dry soil. In other words, what we're determining is we're going to eliminate the moisture from it and say the actual dry density is 3.25 pounds. Now, if we add a little bit of moisture to it, it's going to compact a little bit better. In other words, more material can go into the mold. So what we're going to do is we're going to determine that dry density, and it's going to increase, let's say, to 3.75 pounds in the mold. Now we're going to add a little bit more moisture, and it's going to go up yet again. And let's just say that it goes up to 4 pounds, again, in the mold. Okay? Now, all of a sudden, we add a little bit more moisture, and again, think about the sandcastle. What happens is it begins to fall apart. Why is that happening? Because now we're no longer getting optimum compaction, but we're actually replacing the soil with water. So now the weight begins to go down. So as we calculate that dry density, it goes up, 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 and then eventually we put too much water in it and it goes over the top, and this is what's considered the other side of the optimum. So when we graph this, what we're going to do is we're going to graph the optimum density compared to the optimum moisture. And again, if we think about the sandcastle, what we're doing is we start off at, let's say, 3% moisture. And inside of our mold, we put in 110 pounds per cubic foot of material. Now I know that you're thinking, well, the mold is very small. The mold is exactly 1/30th of a cubic foot. So what we do is we take that weight and divide it by 1/30. Therefore, it'll give us the pounds per cubic foot of material in the mold. So let's say we start off at 3%. We have about 111 pounds per cubic foot of material. We're going to add a little bit of moisture, and that comes up. The moisture goes up along with the density. Then we add a little bit more moisture, and what happens is our density goes up as well as the moisture. And then we're going to add a little bit more moisture, and when we do, we're going to notice that suddenly our dry density begins to drop off. Once this occurs, we are over the optimum compaction limit. And we want to do it again just to make sure that we definitely have an accurate reading. And once we're too beyond the optimum, we can make our determination that this is the optimum. Now, depending upon the application, what the actual control limit is may vary. In some cases, it may be 95% of optimum. In other cases, it may be 93% of optimum, and so on. But what we're going to try to do today is come up to about 93% of optimum, plus or minus 2% on the moisture. So if this is our optimum moisture is 6%. Plus or minus 2% is going to be 4% to 8%, while we're at 93% of the optimum density. So, without further ado, let's go ahead and give this test a shot. What we're doing today is the moist preparation method. This is the preferred method for this particular test. So what we're doing is we're taking our sample, we're going to pass it through a number 4 sieve, because we're using method A. We're going to pass it through a number 4 sieve, and then we determine the moisture content of our sample. Now, we've prepared 5 samples, starting with 2% moisture, and increasing each sample with 3% moisture from there on up through to the end. So what we're going to do now is, starting with our moisture sample of 2%, we're going to go ahead and do one of the tests. So the first thing we want to do is we want to weigh our mold without the collar, because when we reweigh this with the material in it, obviously the collar will not be on the mold.
To follow along, you may want to record this weight. The empty mold weight is 9.01 pounds.
So now we're ready to do the test. So the first thing we want to do is we want to put the collar onto our mold. And we're going to tighten down the collar. Now we're going to fill the mold in 3 equal layers. Now on the third layer, we want to be just about maybe 1/4 of an inch over the top of the mold into the collar. Okay? Once again, we're going to be doing the standard compaction test. Therefore, we're going to be using the 5.5 pound hammer that has a 12-inch drop. We're going to be doing 3 layers, 25 drops per layer. So after our 25 drops on the first layer, we want to fill it a second layer. And then finally our last layer. And once again, we want to go about 1/4 of an inch into the collar. So here, we're going to come just up above the top of the mold. And once again, we're going to now do 25 drops onto the third layer. So now after the third layer, what we're going to do is we're going to go ahead and take the collar off, and we're going to screed off the top of the mold to ensure a nice flat surface.
We can now remove the collar from the cylinder, and as you can see here, we're about 1/4 of an inch above the top of the mold. So we want to go ahead and scrape off the excess, and then we're going to clean the mold before we weigh it.
So now we're going to go ahead and weigh the weight of both the mold and the compacted soil.
Now you may remember that the weight of the empty mold was 9.01 pounds. The weight of the moist soil and the mold is 12.67 pounds. So here we simply want to deduct the weight of the mold, and this tells us that there is 3.66 pounds of moist material in the mold.
Now that we have the weight of both the mold and the moist soil in the mold, we need to get an accurate moisture content on that material. Therefore, the first thing we have to do is weigh an empty bowl. This bowl will be used to put our moist material in and then place in the oven. The bowl weighs 380 grams.
Now we want to get the moisture content of the material. To get a representative sample, we want to disassemble the mold. Then we want to take our sample as near to the center as possible. Here we want to obtain approximately 500 grams of material.
Now that we've gotten our representative sample from the mold, we want to go ahead and weigh both the mold and the sample. In this case, that weight is 880 grams. You may recall that the bowl itself weighed 380 grams, meaning that the moist soil is 500 grams. We now want to dry the sample to a constant mass and be sure to record this weight.
For our example, let's assume that the weight of the dry sample and the bowl was 870 grams, meaning that the dry soil is 490 grams. Now the calculation for moisture content is the moist soil minus the dry soil divided by the moist soil multiplied by 100. Or in our case, 500 grams minus 490 grams divided by 500 grams times 100 tells us that our sample has 2% total moisture content. We now have all the information necessary to calculate our dry density. We have the volume of the mold, which is 1/30th of a cubic foot, or 0.033 cubic feet. We have the weight of the mold, which is 9.01 pounds. We have the weight of the moist soil compacted, that's 3.66 pounds. And we have the moisture content of our soil at 2%. To calculate our dry density, we must first calculate the unit weight of the material. We do this by taking the moist weight of the sample and dividing it by the volume of the mold. Here, our moist sample is 3.66 pounds. We want to divide that by the volume of the mold, which was 0.033 cubic feet, gives us a unit weight of 110.9 pounds per cubic foot. Now, to get the dry density, all we do is remove the moisture. We do this by taking the 110.9 pounds per cubic foot and dividing it by 1 plus the moisture content, which was 2%, giving us a dry density of 108.7 pounds per cubic foot.
Now you may recall that we're looking for the optimum moisture content, and 2% is by no means the optimum. This gives us one data point on our chart. We still have to do this 4 more times, adding 3% moisture each time as we go. But let's see if we can go a little bit faster on the second run. Woo! Well, I'm exhausted.
But the weight of the mold is obviously not going to change. It's going to remain 9.01 pounds. However, the weight of the mold and the moist soil is going to change because our moist soil has more moisture and now compacts better. So the weight of the moist soil and the mold is 12.99 pounds, meaning the weight of our moist soil is 3.98 pounds. And once again, we have all of the information necessary to calculate our dry density. The volume of the mold is 1/30th of a cubic foot. The weight of the mold is 9.01 pounds. The weight of the moist compacted soil is 3.98 pounds. And you may recall at the beginning of the presentation, we said we're going to carefully add 3% moisture to each test. So 2% from the first test plus 3% is going to be 5% moisture in this sample. And now we can calculate our unit weight, which is going to be 3.98 pounds divided by 0.033 cubic feet, gives us a unit weight of 120.6 pounds per cubic foot. And our dry density is going to be 120.6 pounds per cubic foot divided by 1 plus the moisture content of 5% gives us a dry density of 114.9 pounds per cubic foot. Now we have the second data point in our chart, so let's go ahead with our third run. And again, as expected, the mold weight does not change, but also as expected, the mold with the moist soil does increase. Again, because we have more moisture, therefore our soil is coming together better, it is compacting better, and more soil gets in the mold. So now the mold plus the soil weight is 13.27 pounds. And this means that just the compacted soil is 4.26 pounds. And now again, we have all of the data points that we need to calculate our dry density. And don't forget, our moisture content is now 8%. We've increased it by 3% once again. So if we have 4.26 pounds of soil, we're going to divide that by the volume. Gives us a unit weight of 129.1 pounds per cubic foot. And once again, to calculate the dry density, 129.1 divided by 1.08 gives us a dry density of 119.5 pounds per cubic foot. So let's go ahead and plot that data point onto our chart before moving on to run number 4. So run number 4 is complete, and here is our data. Again, the volume of the mold, 1/30th of a cubic foot. Weight of the mold is 9.01 pounds, but here the weight of the mold and the moist compacted soil is 13.22 pounds, and we have a moisture content now of 11%. So the weight of the soil in the mold is 4.21 pounds, which gives us a unit weight of 127.6 pounds per cubic foot. And if we calculate our dry density, 127.6 pounds per cubic foot divided by 1.11, again, the 0.11 is the percent moisture, we have a dry density of 114.9 pounds per cubic foot. And if we take a look at our chart, we can see that our dry density is beginning to drop off. But let's go ahead and do one more run just to make sure that we are indeed beyond the optimum. And for run number 5, again, volume, 1/30th of a cubic foot, weight of the mold, 9.01 pounds. The weight of the moist soil is now at 13.07 pounds, and our moisture content is 14%. And from this, we see that our moist soil in the mold is 4.06 pounds, which gives us a unit weight of 123 pounds per cubic foot, and that gives us a dry density of 107.9 pounds per cubic foot, which is obviously at this point well beyond the optimum. So now let's go ahead and take a look at our control limits. Here we know that we have an optimum dry density of 119.5 pounds per cubic foot and an optimum moisture of 8%. Let's assume that our control limits are 98% of the optimum density at plus or minus 2% the optimum moisture. So now, when we compact in the field, we want our soil to be at least 117.1 pounds per cubic foot and have a moisture content of 6 to 10%. And ladies and gentlemen, this is going to conclude Astm D698, Compaction Characteristics of Soil using the Standard Effort.